As we speak, space exploration missions uncover mysteries that would have seemed unimaginable just a generation ago. Recent quests have revealed exoplanets that defy our typical expectations, some shrouded in thick vapor, others possibly hiding icy pockets beneath their surfaces, potentially teeming with life. But how could life exist beneath a planet's surface, shielded from cosmic radiation yet warmed by sunlight at the same time? And why are we so confident that a planet 100 light years away not only has a water shell, but one that exists in vapor form? Today we delve once more into the unknown, where each world tells us more about where we come from and where we may go next. In recent months, the scientific community started to buzz about something revolutionary: potential evidence of intelligent life beyond Earth. Director Simon Holland, collaborating closely with NASA, recently made a bold statement that astronomers are on the verge of discovering evidence of intelligent life beyond Earth. While he lacks a scientific background, his claims echo findings from multiple science teams worldwide. Holland asserts that using the telescope in the Parkes Observatory in Australia, scientists intercepted an unusual radio signal back in 2019. A narrow band frequency at 982 MHz, focused on a star system just 4.2 light years away, Proxima Centauri. Narrow band signals like this stand out because they're typically not naturally occurring. Most celestial objects emit broad frequencies, but here they detected a distinct isolated tone, a possible hallmark of technology. The signal's characteristics showed a Doppler shift, a sign that it originates from a rotating object. The consistent frequency shift resembles the effect we hear when a police siren passes us, changing its pitch. It indicates movement from a distant planet or star system. With such stability and specificity are unlikely to result from the Earth-based interference. Meanwhile, another research team from Oxford is reportedly preparing to release findings based on the same discovery. According to Holland, these researchers identified transmissions matching what we might expect from extraterrestrial technology. The signals, dubbed Breakthrough Listen Candidate 1 or BLC1, could represent the first traces of technosignatures, a term scientists use to describe evidence of technological activity beyond Earth. Interestingly, the Chinese FAST telescope is also following the hot trail. Reports suggest it's locked on to the same coordinates to verify the source and potentially outpace the Oxford team in publishing results. As the world's largest radio telescope, FAST has the capability to gather even more detailed data. However, scientists are proceeding with caution. A definitive announcement would mark a profound shift in our understanding of the universe. And both teams are racing to confirm and analyze the nature of this elusive signal before making any official statements. Let's circle back to the concept of technosignatures. Technosignatures are humanity's best chance of identifying intelligent life beyond Earth by detecting signals or artifacts that indicate advanced technology. Unlike naturally occurring signals, technosignatures can exhibit structured patterns, specific frequencies, or other markers that suggest a deliberate source that isn't random cosmic noise. The case involving the Breakthrough Listen project is a prime example of this concept. In April 2019, astronomers detected a narrow band signal from Proxima Centauri using the Parkes Mirror radio telescope. The signal labeled BLC-1 initially intrigued researchers because it exhibited several traits commonly associated with technosignatures, such as a narrow frequency band and a detectable Doppler shift. The consistent drift of the signal hinted at a rotating or orbiting transmitter, which is potential evidence of technology. However, a detailed analysis revealed that BLC-1 was unlikely to be extraterrestrial in origin. Its characteristics closely resembled interference from terrestrial sources, specifically an intermodulation product, where overlapping signals from Earth-based sources combine to create a false result mimicking a technosignature. The outcome underscores the challenge of distinguishing genuine technosignatures from false positives. Even signals closely mimicking extraterrestrial technology often require rigorous scrutiny to rule out human interference. Differentiating real signals from noise demands ongoing refinement of SETI methods, especially as we explore increasingly promising frequencies and investigate new types of technosignatures. While we search outer space for signs of intelligent civilizations, the quest to find habitable environments is equally compelling. Identifying planets with suitable atmospheric conditions brings us closer to understanding where life might exist, even if it differs from terrestrial life. Recently, the James Webb Space Telescope made a remarkable discovery in this realm. Just 100 light-years away, in the GJ9827 system, Webb's instruments identified a planet with a heavy, dense water atmosphere. Known as GJ9827d, this exoplanet showcases an atmospheric profile dominated by water vapor, a true steam world. While conditions on the planet are extreme, the discovery hints at the diversity of planetary environments that might one day reveal habitable areas. Scientists suggest that this planet's atmosphere consists predominantly of water vapor. Twice the size of Earth and 3 times as massive, GJ9827d orbits its host star incredibly closely, completing a revolution in just over 6 Earth days. This finding supports long-standing hypotheses that steam worlds could populate other star systems, while life as we know it is unlikely to exist on such a hot, high-pressure planet. This discovery introduces a whole new category of planets to our growing catalog. For decades, astronomers have theorized that steam worlds might form when planets of a certain size retain thick atmospheres, trapping water as vapor and preventing it from condensing. Using a technique called transmission spectroscopy, scientists detected the water vapor by analyzing the planet's atmosphere. As GJ9827d passed in front of its star, starlight filtered through the planet's atmosphere, where each element and compound absorbs specific wavelengths of light, leaving fingerprints in the spectrum. With Webb's powerful near-infrared spectrograph, researchers identified clear traces of water molecules in the planet's atmosphere. This discovery marks a significant leap, as most exoplanets studied to date have atmospheres dominated by hydrogen and helium, similar to the gas giants in our solar system. In contrast, GJ9827d contains heavier molecules, making it one of the few known exoplanets with an atmosphere somewhat resembling Earth's despite its extreme conditions. Scientists, including lead researcher Caroline Piolet-Goriev, believe that this discovery hints at the possibility of finding more steam worlds, suggesting that water-rich planets might be more common than previously thought. The discovery of water vapor on distant exoplanets represents only a small piece of a central theme in space exploration. Where there is water, there could be life. The search for water sources suitable for life brings us closer to home, Mars. Mars, often considered the next frontier for human exploration, offers tantalizing clues about the possibility of life beneath its icy crust. Recent NASA research suggests that organisms could survive in meltwater pools beneath the planet's surface ice, a harsh yet protective environment that might shield microbes from extreme conditions. NASA researchers, led by Aditya Kular, have used computer modeling to demonstrate how sunlight could penetrate layers of dusty ice on Mars, warming it enough to form shallow meltwater pools a few feet beneath the surface. These conditions are akin to Earth's cryoconite holes, small pockets of meltwater within glacial ice that harbor microecosystems with photosynthetic life. The key to this melting process lies in the dust embedded with Martian ice. On Earth, dark dust particles absorb more sunlight than the surrounding ice, creating localized warming that sustains pockets of liquid water beneath the surface. NASA models indicate that Martian dust-laden ice could function similarly, melting from within as sunlight heats the darker dust layers. The study's main takeaway is that dust concentration dramatically alters how sunlight penetrates Martian ice. With dust levels as low as 0.01%, light can reach depths of up to 16 inches, enough to create temperatures conducive to liquid water. As dust content rises to 0.1%, light penetration drops sharply to 2 inches. Still enough for photosynthesis, but significantly limiting habitable depth. This highlights that dust particles in Martian ice are a double-edged sword. They absorb sunlight, but restrict its penetration. Another important variable studied by the team was the size of the actual grains of ice. Larger grains allow light to penetrate deeper because they scatter less light than smaller ones. In simulations of glacier-like ice with larger grains, sunlight could penetrate up to 2 feet. These differences suggest that varying ice types could create microhabitats within Mars' icy crust, with thicker zones suitable for photosynthesis occurring where larger ice grains prevail. The angle of sunlight also affects these radiation zones. Low-angle sunlight, as it occurs on Mars in winter, limits penetration depth, confining habitable zones to the uppermost ice layers. But during the peak of the Martian summer, midday sunlight can penetrate deeper, particularly in areas near steep slopes where sunlight hits more directly. This seasonal effect means potential microbial habits on Mars would experience fluctuating light and heat, possibly becoming active only at specific times of the year. The most promising sites for these meltwater pools are in Mars' tropics, where warmer temperatures and sunlight levels could enable the melting process under certain ice conditions. A layer of ice not only isolates these water pockets, but also provides protection from harmful radiation, a crucial factor given Mars' lack of a protective magnetic field. Based on these findings, researchers are planning future experiments to replicate Martian ice conditions in the lab to better understand how these meltwater pools might support life. Our search for exoplanets goes beyond mere curiosity. It's a mission driven by both a desire for understanding and a need for survival. As evidence of cosmic threats grow, from high-energy radiation to potential asteroid collisions, the search for habitable worlds becomes a proactive measure. It's not just about finding other Earth-like planets, but preparing for a future where we might need to seek refuge beyond our home. The universe also harbors many dangers, such as cosmic rays from unexpected sources. For example, the microquasar V4641 Sagittari, a nearby binary system, has shown that high-energy radiation can originate not only from distant galaxies. Jets from this microquasar emit extraordinarily energetic photons, with radiation sometimes reaching us at much greater intensities than previously anticipated. If intense cosmic radiation can arise so close to us, the need to understand such phenomena and develop protective solutions becomes even more urgent. Alongside cosmic rays, objects like the asteroid Apophis remind us of the direct physical threats to Earth. Apophis, which will pass close to Earth in 2029, has prompted space agencies worldwide to study its composition and structure. The European Space Agency's Ramses mission will approach the asteroid to learn more about its stability and potential risk. Missions like Ramses and NASA's OSIRIS-REx exemplify our efforts to understand and prepare for such close encounters, emphasizing the relevance of planetary defense. However, even as we monitor and mitigate these threats, the search for exoplanets remains a beacon of hope. It's not just about seeking refuge, but discovering entirely new environments that expand our possibilities and resilience. Planets with conditions significantly different from ours may hold resources or even forms of life that could teach us far more than we can currently imagine. In our quest for exoplanets, we confront both our fears and our aspirations, navigating the balance between the risk surrounding us and the dreams of worlds yet unknown. All of us probably watched science fiction films and wondered what aliens may look like. Many people imagine extraterrestrial life similar to us, carbon-based, but with a few biological differences. And others imagine it as something completely unlike humans. And so the famous author of The Laws of Robotics, science fiction writer Isaac Asimov, describes some forms of alien life as living stones that had a silicon-based chemical composition as opposed to carbon like us. But what if we told you that silicon-based life may not be entirely fictional? Today we will delve into our biology and try to answer whether the existence of silicon-based life is possible. Carbon is the basis of our life. Without it, it is possible that we would never have come to exist. It makes up about 18%, or 26 pounds of our total body weight, and performs a structural function, forming something akin to a carcass for the molecules and organic substances necessary for our life. Proteins, fats, carbohydrates, sugars, etc., even DNA. Moreover, as you may know, carbon plays an important role for many life forms around us, such as plants. With each breath out, we exhale carbon dioxide. This gas is required for plants for photosynthesis and the production of oxygen as well as organic substances like glucose. CO2 is also the gas that traps heat in our atmosphere, which sustains all life on Earth. If it weren't for the harmful greenhouse effect, we would simply freeze. Aside from the value of carbon and its compounds in biology, it's important to mention the role it plays in manufacturing. Most of the things you see on a daily basis contain carbon. From clothes, medicine, your favorite cup of coffee, and the house you live in, to musical instruments played by your favorite musicians, and the phone or laptop on which you're watching this video. All of it couldn't exist. Of course, carbon is not the only component present in living organisms and all of the aforementioned items, but its chemical versatility and the ability to build huge chains with other elements makes carbon practically indispensable. According to astrobiologist Robert Hazen, a vital chemical element must be able to actively form bonds with other elements and not be too reactive at the same time, so as not to combust during these interactions. Furthermore, this element must form strong, long-term bonds and be able to store and transmit information. Carbon meets these criteria, and therefore is superior among the most important building blocks on Earth and beyond. However, is carbon really the only possible foundation for life? What if it was simply erased from outer space? What element could then replace carbon? The possible answer can be found right under carbon in the periodic table: silicon. Silicon is one of the most common elements on Earth. Its core contains about 28% of its total mass. This element can be found in sand, amethyst, clay, granite, etc. Like carbon, silicon has a wide range of applications and is a valuable element in our life. Many processors in phones and computers use silicon as an accessible alternative. Silicon is also used to form conformable silicone compounds, which have applications in cosmetic and medical industries, ranging from hair conditioners to contact lenses, as well as aviation and construction spheres, like in sealants and nonstick paint. So what role does silicon play in our biological life? According to researcher Milton Wainwright, it's likely that silicon may have had an effect on the emergence of life on Earth. According to his research, silicon that comes from outer space may stimulate bacteria growth, even if there's a lack of nutrients. The scientists therefore suggest that billions of years ago, during the birth of the solar system, comets containing silicon may have bombarded Earth, which caused the development of bacteria. In addition to its possible merits in the past, silicon is also a very important component in plant development and growth. Silicon protects plants from external threats, both physical and chemical, making them more resistant. It also protects the plants from disease and prevents them from losing water. Moreover, silicon is important for healthy bone development and wound healing in humans and other animals. This element may also reduce the risk of Alzheimer's and cardiovascular disease. You could say that silicon, in fact, has an auxiliary effect on our lives. So why is it being considered as a likely alternative for carbon in alien life? First, it is due to their chemical similarity. There is a reason why silicon is located right under carbon in the periodic table. Each chemical element in the table can form a chemical bond, during which the electrons of each atom are combined. Silicon and carbon are both tetravalent, meaning they can bond to 4 atoms. As such, silicon can probably form long and strong bonds with different elements, similar to carbon. Secondly, in 2016, a team of scientists from the California Institute of Technology, led by Francis Arnold, were able to synthesize molecules that are made entirely of silicon and carbon. Furthermore, according to their study, E. coli could produce the protein that contained this compound. Scientists came to the conclusion that silicon-based life is possible outside of Earth. So, in order to answer the question of whether silicon could replace carbon, we must first consider what life is in biological terms and what are the criteria for it to occur. Scientist Norman Pace believes that life is the ability of an organism to replicate itself and to develop enough to overcome evolutionary hurdles. For example, developing the ability to grow organs required for movement in order to make travel across land easier. Therefore, the building blocks of this organism must be able to quickly adapt to new conditions. In addition to chemical complexity, a number of ecological criteria must be met for life as we now know it to emerge. In short, life requires oxygen, nitrogen, moderate temperatures, and water. Many compounds are highly soluble in water, such as salt. Therefore, previously separate parts of one compound can create new bonds with other elements. Carbon can form a long and stable framework for the living cells of water-based organisms. But can silicon also make connections necessary for life to exist? The short answer is no. So, what? That's it? Silicon-based life cannot possibly exist? Not quite. Because in addition to water, there are other solvents in which life can hypothetically originate. For example, scientists speculate that liquid ammonia, which is common on Jupiter and Pluto, could serve as an alternative to water. However, NH3 is highly toxic, which may prevent silicon-based life from developing, but scientists have yet to test this theory. In addition to liquid ammonia, another potential solvent is sulfuric acid. You may note that H2SO4 is generally capable of dissolving most metals without residue, and you'd be correct, but oddly enough, it's also possible for silicon to develop in it. Therefore, hypothetically, silicon-containing organisms can develop on planets with a sulfuric acid environment, such as Venus. Silicon can also exist in other cold solvents like methane and ethane, which become liquid at low temperatures, as they do on Titan, one of Saturn's moons. However, low temperatures greatly slow down any chemical processes and solubility. Although silicon would be able to quickly combine with other elements at low temperatures, silicon compounds would not be able to dissolve very quickly. Therefore, it would be very difficult for life to emerge in such conditions. But what about the structural function of silicon? Just like carbon, silicon can combine with elements essential for our existence, including nitrogen, hydrogen, oxygen, phosphorus, sulfur, and even many metals. However, silicon is not as versatile and adaptable as carbon. In addition to the fact that silicon cannot develop in water, it will also not bond with anything at moderate temperatures between 32 and 212 degrees Fahrenheit. That means that silicon can only combine with other elements at excessively high or significantly low temperatures, which would make it very difficult for other elements to build bonds with silicon. Moreover, unlike carbon, silicon does not bond well with itself, and that is the bonds between two silicon atoms that would not be able to build a very large framework for cells. Think of a diamond. It's made entirely of carbon, which shows the strength of the compounds the element is able to form. However, the one element that silicon likes to combine with is oxygen. And this further supports the theory that silicon-based life is unlikely. On Earth, silicon is almost always found in the form of SiO2, which is basically sand, making it very difficult to separate the two elements. This means that silicon is less versatile than carbon, which forms equally strong bonds with other elements. Turns out that if we could swap carbon in our body for silicon, then instead of carbon dioxide, we would exhale sand. Aside from respiration, carbon also plays a very important role in our nutrition. Food is an excellent source of energy, which is why when we feel tired, there's nothing better than a good meal. However, our source of energy is not the food itself, but the compounds it contains, like glucose. As you may have already guessed, glucose is also made of carbon. What's more, when we don't have an opportunity to eat and we need energy, another carbon compound like starch can help us. It's deposited into the liver and used to replenish our supply of glucose when needed. However, these bonds would be unstable with silicon, which means they would not be able to properly support our life. While silicon is unlikely to replace carbon, it is possible for silicon-based life to evolve. However, it's highly doubtful that an organism that only contains silicon and no carbon in its chemical composition would be able to build complex chemical bonds. Silicon-based organisms have not yet been found on Earth, but as we've already mentioned, silicon is an important secondary component for many plants and animals. In some ways, it could probably be considered a part of ourselves. Furthermore, our ocean contains diatoms, a type of mysterious algae with cell walls made of transparent SiO2. This doesn't make this algae a silicon-based life form, but it does prove that silicon can indeed act as a building block of a living organism. As for other planets, According to a study by a team of scientists led by Ricardo Gobato, the ideal environment for the development of silicon-based life are the virtual absence of oxygen and water, temperatures above 428 degrees Fahrenheit or below 32 degrees Fahrenheit, atmospheric pressure much higher than on Earth, and a solvent like sulfuric acid or methane. Some of the planets in the solar system fit some or almost all of the criteria. For instance, Titan, the largest moon of Saturn, and possibly Venus. Titan has a multitude of methane and ethane lakes, as well as a nitrogen atmosphere, which are both excellent conditions for the origin of silicon-based life. The surface of Venus is very hot and subject to high pressure. However, the thing that makes Venus one of the candidates for silicon-based life are yellow clouds of sulfuric acid present on the planet. Hypothetically, silicon organisms could form in these clouds, although most likely, even on Venus, a molecule like that would contain significantly more carbon than silicon due to the high content of carbon in the atmosphere. Surprisingly, another candidate for the formation of silicon-based life are hypothetical carbon planets. At the moment, scientists only know of one such exoplanet, 55 Cancri e, which is located 40 light-years away from Earth. These planets likely form further from their parent star, which means they may have solvents suitable for silicon on their surface, and hypothetically, no water either. Moreover, it is possible that carbon planets are full of heavy hydrocarbons like butane, which may be suitable for silicon-carbon bonding. However, silicon-carbon compounds, silicon carbide, are very strong, which means their decomposition can take a lot of time and energy. So even if life begins to develop on a carbon planet, it will be a very long process. If we assume that silicon-based life has in fact existed for some time, then how would we recognize it? Sci-fi writers imagine a life form similar to living stones, like the authors of the Star Trek, for example.
We are dealing with a silicon creature of the deep rocks.
However, in reality, silicon-based life does not necessarily look like this, since we are also not covered in diamonds and diatoms look nothing like stone. The fact of the matter is, scientists have no idea what a silicon-based life might look like. However, they assume that silicon-based life is unlikely to resemble us in chemical complexity or even intelligence, so we probably won't get to meet stone people. Such alien organisms would also be difficult to find if not technologically advanced, because we simply would not know what molecules to look for. It is difficult for humans to imagine the possibility of life developing in conditions that are significantly different from those on Earth. The only life we've encountered so far is ourselves and the creatures surrounding us, which is why most missions sent into space focus on finding structures similar to our own. Right now, it's impossible for us to know if there is life made predominantly of silicon due to our scientific limitations. However, the cosmos is vast and diverse, so we cannot say for certain whether all alien life in billions of galaxies is carbon-based. For centuries, we have looked to the heavens, fascinated by the possibility of life beyond Earth. But what if our search is limited not by the technology we possess, but by the assumptions we make about life itself? What if the key to unlocking this cosmic mystery is hidden in plain sight, in a substance so common but so overlooked? Imagine a world where rivers flow not with water, but with pungent-smelling liquid. A place where the building blocks of life are not carbon molecules floating in water, but complex structures thriving in a sea of ammonia. It sounds like science fiction, but scientists are taking the concept of the existence of ammonia-based life forms more and more seriously. Ever since telescopes reached the stars, humanity has been consumed with the search for life beyond Earth. We've sent rovers to Mars, probes to Venus, and even peered into the icy oceans of Jupiter's satellite Europa. But all these efforts have been guided by a single assumption. Life, wherever it exists, must be something like us, carbon-based and dependent on water. This is where the concept of the Goldilocks zone comes into play. This is a neither too hot nor too cold region around a star where conditions are just right for liquid water to exist. For decades, this zone has been the center of our extraterrestrial search, the celestial point where we believe life is most likely to thrive. From the Viking landing modules on Mars to the Voyager probes traveling beyond our solar system, the hunt for extraterrestrial life has been a hunt for Earth-like conditions. We look for planets with atmospheres similar to our own, signs of water or ice, and even certain gases such as methane and oxygen that might indicate biological activity. But what if this geocentric approach has narrowed our vision? What if, in our search for a mirror of our world, we've overlooked vast expanses where life might exist, but in forms radically different from our own? It's a humbling thought that challenges the very structure of astrobiology. After all, if life can exist without water, then the Goldilocks zone is not the only area in the cosmic real estate market where life can settle. And that brings us to ammonia, a molecule that has long been relegated to the background but is now taking center stage in a potentially game-changing way in our search for life beyond Earth. Did you know that ammonia, a compound you might associate with cleaning products, has a lower freezing point than water, enabling life in an extremely cold condition? Or that ammonia can dissolve a wide range of organic compounds, potentially serving as a medium for various types of biochemical processes? When we think of life, we often envision Earth's blue-green tapestry, forests teeming with wildlife, and oceans filled with a multitude of marine life. But what if there are shades in the palette of life that we haven't even realized? What if beyond the azure oceans and emerald forests there are worlds where life thrives in a golden sea of liquid ammonia? So, venturing beyond the familiar territories of carbon and water, we encounter a molecule that has long been in the shadow of astrobiology, ammonia. This humble molecule, composed of just one nitrogen atom and 3 hydrogen atoms, may hold the key to a life form quite different from our geocentric definitions. At first glance, ammonia seems an unlikely candidate for life support. After all, we're used to thinking of it as a caustic gas, a household cleaner, or an industrial chemical. But when we delve deeper into its chemical properties, a different picture emerges. Like water, ammonia is a polar molecule capable of dissolving a wide range of substances. It can act as a solvent, facilitating complex biochemical reactions, just as water does on Earth. However, ammonia operates under different rules. It has a lower boiling point and a lower freezing point than water. This means that life based on ammonia will exist at temperatures much lower than any earthly organism can tolerate. Imagine a world where the average temperature is well below freezing, but life thrives in oceans of liquid ammonia. Such a world would not only have a different biochemistry, but also different color palette. The sky may have shades of orange and red, and the seas may shimmer with hues of gold or bronze. very different from the blue and green landscapes we associate with habitability. And just as there is a water cycle on Earth, an ammonia-based world will have its ammonia cycle, complete with ammonia clouds, ammonia rain, and perhaps even ammonia snow. This active cycle would be essential for any potential life forms, providing a dynamic environment for development. If life can exist in Earth's extreme environments, from acidic lakes to deep-sea hydrothermal vents, why not in the ammonia-rich landscape of distant exoplanets? This possibility has the potential to rewrite textbooks and push the boundaries of life as we know it. As we delve deeper into the realm of alternative biochemistry, it's critical to distinguish between two key components of life: carbon and water. While both are essential for life on Earth, their roles are distinct, and understanding this difference is crucial when we consider the possibilities of ammonia-based life. First, let's talk about carbon. Carbon is the basis of all known life forms, a versatile element capable of forming complex, stable structures such as proteins, lipids, and DNA. Its ability to form four bonds makes it uniquely suited to create the complex molecules that are the building blocks of life. Now let us consider water. Water acts as the stage on which the drama of life unfolds. It is a solvent that facilitates biochemical reactions, allowing molecules to meet, interact, and transform. In essence, if carbon is the actor, water is the theater itself. So what happens if we replace one of these key players? Replacing carbon would mean rethinking the very building blocks of life, a feat that seems almost insurmountable given carbon's unique properties. But what happens if we replace water with ammonia? That's a different story. Ammonia can also act as a solvent, albeit in a colder temperature range, offering an alternative step in the biochemistry of life. As with water, the polarity of ammonia allows it to dissolve various substances, making it an acceptable alternative for facilitating biochemical reactions. However, because of the lower temperatures, reactions are likely to be slower, potentially leading to life forms with a slower metabolic rate. In an ammonia-based world, cells may have membranes composed of lipids stable in ammonia and enzymes that catalyze reactions in this alternative solvent. The genetic material may still be similar to DNA or RNA, but adapted to an ammonia-rich environment. So when we ponder the possibilities of life beyond Earth, the question is not only where to look, but what to look for. Let's delve into the biochemistry of an ammonia-based life form. In such an organism, the role of water as a solvent would be replaced by ammonia. What about the biochemical reactions themselves? Can the enzymes and proteins that facilitate life processes in aquatic organisms adapt to an ammonia-rich environment? The answer is staggeringly possible. Enzymes, biological catalysts, may have evolved to function at lower temperatures and in the unique chemical environment provided by ammonia. These enzymes may be composed of amino acids stable in ammonia, allowing metabolic processes to occur, albeit at a slower rate due to the colder conditions. But what would these life forms look like? In an ammonia-based world, we might find organisms with biochemistry and physiology radically different from our own. Imagine creatures with flexible, elastic skeletons, adapted to lower gravity and lower temperatures, or plants that use a different pigment for photosynthesis that absorb and uses light more efficiently. For example, a pigment that absorbs blue or violet light may be more efficient if a planet orbits a star that emits light predominantly in those wavelengths. In designing future space missions, these considerations could be critical. Instruments capable of detecting not only water and oxygen, but also ammonia and other biosignatures, would expand our search parameters and allow us to explore these exotic possibilities. Of ammonia-based life go far beyond scientific curiosity. They could fundamentally alter our approach to the search for extraterrestrial life by changing the strategies and technologies we use in this great cosmic quest. So far, the parameters of our search have been strongly influenced by our geocentric perspective. We've aimed our telescopes and sent probes to places where we expect to find Earth-like conditions. But if ammonia-based life is possible, then our search field expands exponentially. This means rethinking mission objectives and scientific instruments. Future space probes may have to carry detectors sensitive to ammonia and other non-aqueous solvents. Spectrometers may have to be calibrated to look for unique spectral characteristics of ammonia-based biomolecules. Imagine a new generation of Mars rovers designed to probe the icy satellites of Jupiter and Saturn, not only for water, but for pockets of liquid ammonia. Or orbiters equipped with advanced sensors that can analyze the atmospheres of exoplanets in search of chemical imbalances that might indicate ammonia-based biological activity. The discovery of even ammonia-based microbial life would be a revolutionary event that would leave a lasting impression on the world and change our philosophical and ethical foundations. How would such a discovery affect our understanding of the uniqueness and commonality of life in the universe? What ethical considerations might arise from interacting with or studying these alternative life forms? Education will also transform. Future biology textbooks may include chapters on alternative biochemistry, and astrobiology may become a standard part of educational programs, inspiring a new generation of scientists to think beyond Earth's limits. As we stand on the threshold of this new frontier, the implications of recognizing ammonia as a potential cornerstone of life are enormous. It broadens our horizons, challenges our assumptions, and opens up a universe full of possibilities. Possibilities that may start with a simple molecule, but lead us to worlds beyond our wildest imagination. Are we alone in the universe? Those involved in the search for extraterrestrial life have been increasingly sharing the view that mankind is not ready for contact with the alien civilization. It becomes obvious the moment we put the dreams and imagination aside and delve into the scientific approach. Not only can the search for intelligent civilizations be fruitless, but it can also lead to opening the door that we are not ready to walk through. What mysteries actually hide behind the cosmic silence? And why do we put so much effort into coming in contact with extraterrestrial beings, knowing that we may never achieve this goal? After spending years exploring the possibilities of coming into contact with extraterrestrial beings, scientists had come to surprising conclusions. Let's imagine that alien civilization is at the same level of technological advancement as us, and their spacecrafts fly at the same speeds as ours. Turns out intelligent life with this advancement level needs less than 1 billion years to spread across a galaxy of the same size as ours. Just look at how fast the galaxy would actually have been inhabited by any civilization of this caliber. But if that were the case, why are we not seeing this lively galaxy around us? To answer this question, we'll need to take a look at the Kardashev Scale. The majority of modern scientists use this scale to measure the potential ability of living organisms to colonize the surrounding space and subsequently the possibility of contact with other life forms. This scale gives its own answer as to why we are not seeing this image of populated space all around us. Kardashev proposed to measure a civilization's level of technological advancement based on how efficiently it uses their energy resources. According to this scale, a Type 1 civilization can learn to utilize all of the energy that they're able to harvest on their home planet, radiating from its parent star. This type of civilization is most likely ready for interplanetary travel and at some point down the line will be able to colonize its entire system. For context, we only use 73% of the planet's energy potential, whereas the amount of energy we learn to harness from the sun is less than 0.1%. Turns out we're still on level 0, according to this scale. Civilizations that have reached the status of Type 2 are capable of capturing the energy not only on their home planet, but also any energy they could harness within their star system. Or at the very least, they're close to being able to do that. In their search for this type of civilization, scientists are on the lookout for a Dyson sphere, a hypothetical artificial structure that would allow the civilization to harness all of the star's energy from within the system. These civilizations would be capable of interstellar travel. They will have actively colonized their own galaxy and possibly moved on to colonizing the surrounding areas, which would allow them to keep increasing the amount of energy that they could use. As well as using all of the energy of their star system, Type 3 civilizations are able to harness the energy from neighboring systems, control the energy of their entire galaxy, or even the entire universe. These civilizations are able to not only control this energy, but possibly change entire worlds. There's a simple reason as to why communicating with the Type 1 civilization is problematic. Upon calculating the capacity at which we can transmit and receive signals in space, we come to find that the maximum visibility of the Earth's energy activity, radio signals, lasers, electric activity, is very limited. We can only be seen or heard from a distance of 4 light years. The noise we create could only be heard by our closest neighbors who have reached the same level of development. Type 2 civilization would be able to hear us from much further away. They would also be able to ensure they remain unnoticed, either because of the great distance or because they wish to keep it that way. After 60 years of transmitting various signals and scanning the skies trying to detect artificial signals, we haven't been able to find anything and we remain unheard. The paradox of great silence was first raised by legendary physicist Enrico Fermi. Speaking to his colleagues once, he raised a seemingly simple question. Where are the aliens, and why have they not been to visit us? However, when you consider our civilization's level of development, the answer is pretty obvious. Why would they? The logistics required for interstellar travel are only available to civilizations that have reached Type 2 at least, and in their eyes, we're not worth it. What person in their right mind would try to communicate with ants? How would an ant be able to recognize that someone's trying to communicate with it? After all, in terms of our development and technological advancement, compared to them, we're akin to highly developed ants that have taken over an entire planet, not to mention the ineffective use of said planet's potential. Other civilizations that, like us, haven't yet reached Type 1, they stay confined to their own planet and star system. It's simply unrealistic to expect any guest from a place like that. It is possible that right at this moment they're working on the same problems as we are. Starvation, fighting for resources, and pursuing minor and major wars for territories. And so it appears that Type 1 civilizations would simply have other things to worry about. However, is it possible that someone could have overcome those issues and decided to launch themselves into space? The data presented by the scientists suggests we may in fact have a surprisingly large number of neighbors. As we lift our gaze to the cloudless sky, we can imagine how many potential inhabited planets there are. What we see in the sky is only 1% of our own galaxy, the Milky Way. Even if only 1% of these worlds are inhabited and populated with conscious life, that would amount to around 100,000 intelligent civilizations that could exist in our galaxy alone. And they all remain silent. There are a vast number of solutions to the Fermi's paradox because there are around 100 scientific theories alone that attempt to explain this silence. Let's break down the most interesting of those theories. There are no signs of Type 2 or Type 3 civilizations because they don't exist. The scientific analysis tells us there are thousands of civilizations in our galaxy alone, hence they presume that there is a factor that stands in the way of their development. This factor is called the Great Filter. This theory suggests that after reaching a certain level of development, life faces an obstacle that's impossible to overcome. However, scientists don't know what this Great Filter may be. The possibilities are only limited by our imagination, from artificial intelligence, which cleanses the overly developed organic life from the galaxy, to various forms of apocalypse. The most unfortunate thing about this theory is that, if true, humanity is faced with three possible prospects in the future. According to the first scenario, we as humanity are a unique life form that has managed to overcome the big hurdle of the Great Filter. That would mean that reaching our level of progress is very challenging, and the chances of it happening are very low. In this case, the cosmic silence would be caused by the majority of civilizations failing to overcome the Great Filter. Hence, we simply have nobody to come in contact with. The second scenario suggests that we happen to be the first ones among our neighbors to advance to this level. This would be due to the fact that the conditions necessary for the existence of conscious life had only been established relatively recently, and we happen to be the pioneers of this progress. In this case, we simply found ourselves in the right place at the right time to have become one of the first ultra-intelligent civilizations. It also means we have plenty of time to advance to become a Type 2 and Type 3 civilization. That's the reason why there's no hope for contact. We are progressing faster than any other organic form of life since the Big Bang. The third scenario presented by scientists is more pessimistic. They reckon that if we were not the first ones to reach this level of advancement in this rare sequence of cosmic events, then the Great Filter is still ahead of us. They think that life evolves at regular intervals until it reaches a certain stage, which is where we stand now. Whatever or whoever it is, it presents a challenge that prevents life from evolving to a Type 1 civilization, and it's unlikely that we would be an exception to this rule. Those favoring the third hypothesis believe that the cosmic silence is great news for us. After all, the presence of complex life on Mars, Moon, or somewhere else means that the Great Filter is bound to be ahead of us. There's also an opposing viewpoint. According to it, Type 2 and Type 3 civilizations do exist, and we haven't come across them for a reason. This is based mainly upon the fact that we're very much limited in our search. After all, we are searching for the signals that are only 100 light years away from us, which represents a mere 0.1% of our galaxy. The most interesting theories resulting from this version sound like this. Galaxy has long been colonized, and to the colonizers themselves, we are located in a low-interest deserted area. The perfect example of a similar situation happened in Earth's history: colonization of North America. Native Americans residing in the remote parts of the continent only learned about the presence of their neighbors, super-developed Europeans, several decades after the latter arrived on the continent. It's also possible the activity is present around our system. We're simply too primitive to understand these signals, or we are focusing our efforts elsewhere. That would be like trying to communicate with people using the internet via Morse code. It is equally possible that our minds differ so greatly compared to other life forms that our attempts to establish contact come across as senseless noise. Another interesting hypothesis is the cosmic zoo theory, which states that we are actually surrounded by a densely populated galaxy. Within this world, Earth is something akin to a wildlife reserve, the kind you could watch, but you're not allowed to go on a safari ride or make contact with such a primitive life form. And still, every attempt to explain this paradox inevitably comes to a stop. We still know very little about space, and we have not yet evolved to the level necessary for resolving these problems. But that doesn't mean that our attempts to find intelligent life have stopped, and humanity is frozen in place, waiting for outside contact. There are currently at least 2 projects that have spent several decades trying to establish contact and search for extraterrestrial life. These are the projects SETI and METI. The work of these 2 projects is based on the Drake equation, a mathematical formula that suggests it's possible to accurately calculate the number and, more importantly, the potential location of inhabited worlds. The next step is to use this information to reach out. According to this equation, our galaxy hosts between 8 and 2,900 systems of intelligent life. As science evolved and our knowledge about our galaxy grew, the calculations became more precise. Realistically, there should be 36 other brother worlds coexisting with us in the Milky Way galaxy. The SETI project started in 1984, and at first it focused on scanning our immediate surroundings in search of artificial radio signals coming from our potential neighbors. However, no signals were found. Right now, the major hope is that the European Space Telescope Gaia will bring some results. It's able to transmit information about the exact location of all stars in our galaxy and give an accurate assessment of every star system's potential. That's why the SETI project was able to move on from a rough estimation of various star systems to a detailed analysis of each one, thanks to a technological advancement. And now, every signal sent out there is directed towards the systems with the highest likelihood of intelligent life. Will we get a response from any of them? The answer to this is both yes and no. Some of the systems we have already researched are so far away that any response from them would take over 3,600 years to reach Earth. And last but not least, the mission of METI is also very important. After all, they help by trying to capture any messages from space and send our greetings to distant stars. We know of at least 8 attempted communications, 2 of which are the famous gold records on the Voyager probes and similar ones on the Pioneers. The other 6 are messages contained in radio signals directed towards some stars. For example, to one of the nearest solar-type stars, Gliese 581. So far, there have been about 40 radio sessions in total. We're unlikely to hear a response to them, but it is possible that our descendants might. To sum up the results of our small study, we can say quite definitely that the silence of the universe is normal. It's also possible that we have not yet sufficiently evolved to make contact with the intelligence around us, or even that the cosmos itself is not yet ready for this. Which one of these scenarios is the most likely? Are we a unique species, or has the entire space been colonized by super-developed civilizations for a long while? We are close to uncovering the answers to these questions. But are we ready for this contact? One of Jupiter's mysterious moons, Europa, hides a secret beneath its frozen crust. There's an immense global ocean, potentially teeming with life, sealed and hidden away in darkness for millennia. Recently, NASA launched its Europa Clipper mission, which is yet to unravel the mysteries of this alien world. Beneath the frozen surface, hydrothermal vents may create ideal conditions for life forms to thrive. They do in the deepest parts of Earth's oceans. But how do we explore these extraterrestrial worlds, and what secrets might they reveal? Europa Clipper is one of NASA's most ambitious endeavors, aimed at studying the habitability of icy moons. It was launched in October 2024. It was built to study Europa, one of Jupiter's moons long suspected to harbor a huge subsurface ocean beneath its thick, icy shell. The Clipper mission is set to reach Europa in the 2030s, and its primary goal is to assess whether this moon can support life as we know it. Equipped with top-of-the-line tools, the spacecraft will embark on a multi-year journey through the solar system. Once it reaches Jupiter's orbit, Europa Clipper will make dozens of close flybys of Europa, gathering unprecedented data about its structure, composition, and most importantly, the possibility of life on this moon. The mission's particularly significant because for the first time, a spacecraft will focus on the viability of an oceanic world, expanding our understanding of where life might potentially exist in the universe. Though Europa's surface may seem frozen and uninhabitable, it could be one of the most promising life-sustaining environments beyond Earth. Beneath its icy exterior lies a global ocean potentially holding more than twice the volume of Earth's oceans. It's theorized that the thick ice layer shields the ocean from harsh radiation, while tidal forces from Europa's proximity to Jupiter cause significant flexing and heating, possibly keeping the water in a liquid state. On board Europa Clipper is an impressive suite of scientific instruments, each designed for specific tasks. The ice-penetrating radar will help scientists measure the thickness of the ice and determine if there's any interaction between the ocean and the surface. The spacecraft's spectrometers will be used to analyze the chemical composition of the surface, examining it for compounds that might hint at biological processes. Meanwhile, magnetometers will map Europa's magnetic field, providing clues about the ocean's depth and salinity. Thanks to these repeated flybys, Europa Clipper will be able to provide researchers with detailed insights into the icy shell, the ocean, and the potential hydrothermal activity of this moon. The data gathered by the mission will be crucial in determining whether Europa's ocean contains the chemical energy necessary to sustain life. However, Jupiter's radiation poses a significant challenge for any spacecraft in its vicinity. The planet's magnetic field is 20,000 times stronger than Earth's. It traps charged particles that race around the system at incredible speeds, creating an intense radiation zone bombarding nearby moons with ionizing radiation, including Europa. For Europa Clipper, the challenge lies not only in surviving this high-energy environment, but also in protecting the delicate onboard electronics from being damaged by the radiation. The electronic systems of the craft, including the central computing units, scientific tools, and communication systems, are shielded from radiation. The protective casing, made from a combination of aluminum and zinc, is a vital defense against radiation exposure. But even with this protection, Jupiter's radiation is so intense that some components, particularly the transistors used in Europa Clipper's instruments, may still prove to be vulnerable. Transistors known as MOSFETs, metal oxide semiconductor field effect transistors, are essential for controlling the flow of electricity throughout the spacecraft. These components are especially sensitive to ionizing radiation, which can alter their electrical properties and lead to failure. Recent tests have shown that these transistors fail at lower radiation doses than initially predicted, and that raises concerns about their reliability once Europa Clipper reaches Jupiter's orbit. To mitigate the risk, NASA engineers are running through tests to assess how many transistors could go out of commission during the mission and how severe the consequences might be. They're exploring ways to extend the life of these components through software and operational workarounds, such as limiting exposure to the highest radiation zones and using redundancy in systems where possible. Despite the precautions, there's no simple solution. The spacecraft's electronics vault was sealed in 2023, making any hardware changes impossible without significant delay. Over the last few months, the mission team has been weighing the risk of semiconductor vulnerability against the high cost and potential delay associated with unsealing the vault and replacing parts. If the electronics stop working prematurely, it could jeopardize the operation of critical systems. However, the mission's design includes built-in redundancies and operational flexibility, allowing the team to work around certain failures by relying on backup systems. NASA's task is to ensure these failures do not impede the mission's primary scientific objectives, especially the exploration of Europa's icy surface and the ocean beneath it. Now, let's take a closer look at these oceans. So, as we've already mentioned, there are vast oceans hidden beneath the icy shells of Europa and Enceladus, potentially some of the most promising places for finding life beyond Earth. It's believed that these concealed oceans, kept in a liquid state by the tidal forces of their parent planets, contain key ingredients necessary for life: liquid water, energy sources, and essential chemical elements such as oxygen. But how exactly could we measure the potential for life in these alien oceans? The answer lies in how oxygen and other chemical elements are produced and distributed beneath the icy layers. On Europa, one of the most important factors for assessing habitability is oxygen. Although Europa is constantly bombarded by high-energy particles from Jupiter's magnetic field, this radiation is more than just a threat to technology. It could also contribute to oxygen production. When these charged particles collide with Europa's icy surface, they break water molecules into hydrogen and oxygen. While most of the hydrogen escapes into space, some of the oxygen remains in the Moon's atmosphere or enters the subsurface ocean through the cracks and brine channels in the ice. The current theory is that this water-splitting process is one of the main ways oxygen enters Europa's ocean. However, recent studies have shown that previous estimates of oxygen production on Europa may have been overstated. New data, particularly the measurements taken by NASA's Juno probe, indicate that the amount of molecular oxygen present around Europa is much lower than previously believed. This data suggests a more limited oxygen entry into the subsurface ocean, potentially narrowing the range of conditions in which life could exist. According to the latest data, Europa produces around 26 pounds of molecular oxygen per second. That's a far cry from the earlier estimate of up to 2,000 pounds per second. This revised figure has led scientists to reconsider the question of how much oxygen actually reaches the ocean and whether this amount is sufficient to support oxygen-dependent life forms. Despite the lower than expected oxygen production numbers, Europa remains a prime candidate for harboring life. Even at these low levels, this Jupiter moon produces enough oxygen to sustain life in a unique, potentially energy-efficient form. The process is occurring on Europa, where oxygen may seep into the ocean through cracks in the ice, may resemble Earth's deep-sea environments, where life exists without sunlight, relying on chemical energy. In particular, this energy could be provided by hydrothermal vents on the ocean floor. Hidden beneath thick ice in eternal darkness, these vents may offer chemical and thermal energy supplied by hydrothermal activity, just as hydrothermal vents discovered in Earth's deep oceans. These vents, acting as natural chimneys, release mineral-rich heated water from the rocky depths of the moon, creating a potential haven for the emergence and flourishing of life. On Earth, hydrothermal vents are home to unique ecosystems that don't rely on sunlight. Instead of depending on photosynthesis, the life forms around them derive energy from a chemical reaction between water and minerals, a process known as chemosynthesis. Astrobiologists believe that if life exists on this moon, it could thrive in a similar way. Unlike Earth's deep-sea black smokers, which are powered by the planet's molten core and can reach temperatures over 700 degrees Fahrenheit, hydrothermal vents on these icy moons are expected to be much cooler. The absence of a molten core on Europa and Enceladus raise questions about the sustainable existence of high-temperature vent systems. However, new models suggest that low-temperature hydrothermal vents may have persisted on these moons for billions of years, providing long-term stability and a source of heat. These low-temperature vents should operate similarly to those found on Earth's seabed, for example, along the Juan de Fuca Ridge in the Pacific Ocean. On Earth, cold seawater is drawn into the seabed, where it circulates through ancient volcanic rocks, gradually heating up before re-emerging through other vent openings. This process not only heats the water, but also alters the chemical composition, producing the necessary ingredients for chemosynthetic life. Organisms like tube worms and extremophiles thrive by utilizing hydrogen sulfide and methane released from the seabed. Europa is intriguing not only because of its hidden ocean, but also due to its dynamic surface activity. Recent observations, particularly from NASA's Juno mission, have provided new insights into the water plumes, jets of vapor escaping from beneath the moon's icy crust. These plumes, first spotted by the Hubble Space Telescope and now confirmed by multiple missions, give scientists a tantalizing glimpse of what lies beneath Europa's frozen shell. When the Juno spacecraft went past Europa in 2022, it captured high-resolution images of the Earth's surface, revealing complex features such as ridges, chaotic terrain, and scars that may indicate regions of recent activity. Also, the most significant findings were areas believed to be the source of water vapor plumes. These towering jets shooting as high as 120 miles into space are thought to arise from cracks in the icy crust where salty liquid from the subsurface ocean meets the near vacuum of space and quickly evaporates. Studying these eruptions is crucial for several reasons. Firstly, the substance expelled from Europa's interior can be directly analyzed by the instruments on the passing spacecraft. This gives scientists a unique opportunity to examine the chemical composition of the subsurface ocean without the need to drill through a thick layer of ice. These plumes may contain a mix of water, salts, and possibly even organic molecules. By measuring the chemical composition of the vapor and particles in these plumes, scientists hope to gain deeper insight into the ocean's potential to sustain life. Detecting key elements such as oxygen, methane, or even amino acids would be a significant indicator that Europa's ocean contains the necessary ingredients for life. The composition of these plumes may also reveal the salinity of the water and the interaction between the ocean and the rocky seabed. Both are crucial factors for determining habitability. In addition to plumes, certain regions on Europa's surface, such as the platypus, suggest that liquid water might be closer to the surface than previously assumed. The chaotic terrain of the platypus is a disordered cluster of ice blocks and ridges, likely formed by the seeping of salty water from below the surface and the alteration of the ice surface. This feature, measuring 23 by 42 miles, is considered geologically young, hinting at ongoing activity beneath Europa's frozen crust. Surface activity on this moon continues to provide important clues about what might be happening under the ice. These eruptions not only offer insight into the composition of the subsurface ocean, but also provide valuable information about the processes driving this activity. Processes that may resemble conditions on early Earth. Meanwhile, Europa's surface is dynamic and constantly changing under the influence of Jupiter's powerful gravitational forces. The moon's icy crust is composed of large, rigid plates that float above the subsurface ocean, moving and interacting not unlike the tectonic plates on Earth. These movements create fractures, ridges, and chaotic terrain, altering the surface and possibly affecting what lies beneath. Other research of these same recent images of the platypus feature captured by Juno has revealed intriguing details about the behavior of Europa's ice plates. In this case, the point of interest is a complex arrangement of ice blocks, which suggest ongoing surface processes. These blocks, some reaching up to a kilometer across, are separated by cracks, indicating that the plates may shift or rotate. It's theorized that this activity is caused by the constant tidal flexing that Europa experiences as it orbits Jupiter. As these icy plates move and break apart, they may create pathways for the subsurface ocean water to reach the surface. In some regions, this process could lead to water seeping through the cracks, depositing dark, low albedo material, which may serve as potential evidence of salty liquid emerging from below. By comparing the latest images from Juno with the older data from the Galileo mission, researchers have noted potential changes on Europa's surface. The southern region of the platypus appears wider in the Juno image, and the morphology of the block beneath the eyes looks different in the two data sets, suggesting surface evolution. Although these signs of changes that took place since the Galileo mission are not definitive due to differences in image quality, they may suggest ongoing geological activity. The interaction between the plates may have led to localized melting of ice, or even the emergence of new surface features as salty water from the ocean rises and freezes. Understanding these surface processes is critical, as they directly impact the possibility of accessing samples of subsurface material without drilling through Europa's thick ice shell. If these ice plates regularly move and crack, it could provide a natural pathway to the ocean beneath. Europa and Enceladus. Both of these icy moons are amongst the most promising candidates in the search for extraterrestrial life within our solar system. Now let's summarize. What exactly are the signs of life we should expect to find? And how do Europa and Enceladus compare in their potential to support life? One of the most significant potential signs of life on these moons is the water vapor plumes erupting from their surfaces. On Enceladus, spectacular geysers shoot water, salts, and organic compounds hundreds of miles into space from its south pole. These plumes serve as direct evidence of a subsurface ocean in contact with the moon's rocky core, a crucial factor for sustaining life. On Europa, indirect signs of similar plumes have also been observed. Both moons are also suspected to have hydrothermal activity in the depths of their oceans, where heat and chemical energy are generated as a result of interactions between ocean water and the rocky core. On Earth, these kinds of environments teem with life, suggesting that similar processes on these icy moons could support microbial ecosystems. While the plumes on Enceladus provide easier access to samples from the chemical makeup of the ocean's depths, Europa's thicker ice shell might conceal more complex, long-term interactions between the surface and the ocean, making it equally intriguing for future research. The Europa Clipper mission, launched in October of this year, is a critical step in this search. Although the spacecraft will not land on Europa itself, it'll conduct approximately 50 close flybys, collecting data to determine whether Europa's environment can support life. Europa Clipper's instruments will analyze the moon's icy surface, measure the thickness of its ice shell, and study the composition of the subsurface ocean via its plumes and the chemical makeup of the surface. Signs of life on Europa and Enceladus are likely to be subtle, but if amino acids or other organic compounds are discovered, it may serve as compelling evidence that these moons are habitable. Recent studies suggest that biosignatures on Enceladus may be preserved at much shallower depths, making it easier for future missions to detect them without extensive drilling. On Europa, where the ice shell is thicker, scientists have estimated that amino acids may be preserved beneath the surface at greater depths than previously thought, especially in areas shielded from radiation. Discoveries made by Europa Clipper could pave the way for future missions, including potential landers built to dig deeper into the ice and access the aforementioned preserved biosignatures. Landers could directly sample the ice, study the subsurface layer for chemical signs of life, and even explore active plume regions to capture materials from the ocean beneath. Europa Clipper has already embarked on its journey, and the stakes are high. This mission will not only provide a clearer understanding of this distant world, but also serve as a model for future missions to explore the icy moons of our solar system. Whatever Clipper discovers may very well change our perception of life in our universe and certainly open new horizons for exploration, revealing whether life has found a way to thrive in the hidden oceans of distant worlds.